So I think we can start. No more people. So we have Michael Mulligan that will talk about disentangling topological states with entanglement negativity. Please.
Okay, so hi everyone. It's a pleasure to be there, even if remotely. I'm sorry I can't attend in person, but I'm really happy to be able to speak. So I'm gonna tell you about some recent work with Pak Lim, Hamed Asasi, and Jeffrey Teo, and it's about studying entanglement in various topological states. And as far as I understand, this is an experimental implementation of what I'll be discussing today. So the subject of my talk are quantum Hall states. And the type of rough question I want to think about is, well, what are the types of entanglement in there? So I mean, 2-particle entanglement, 3-particle entanglement, or 3-part, and so on. All right, and how can we use that to try to get a better understanding of these sorts of states? So the states, and these sorts of measures, these non-local entanglement measures, the idea is that they go beyond sort of conventional, say, linear response or transport measurements, as beautifully illustrated in this experiment. So the specific states I'll roughly be thinking about, at least candidate states, are ones that are occurring around filling fraction 5/2 and a close cousin of this guy at filling fraction 4/3. Okay. So one of the, I guess, defining characteristics of a topological phase in 2+1 dimensions is topological degeneracy. So for example, if you take the nu equal 1 over m, where m is an integer Laughlin state, or if you prefer U1 level m, Chern-Simons theory, it has its ground state manifold is degenerate. It has a degeneracy which is m to the g, where g is the genus of space. So, excuse me. So such phases which have a non-trivial degeneracy, that is degeneracy bigger than 1, are said to be long-range entangled. That's one definition. On the other hand, phases without such a degeneracy, so just the integer state above when nu is equal to 1 or some other integer, those are sometimes said to be short-range entangled. Okay, so I want to try to develop a better understanding of these terms, short and long-range entangled. So the tool, as I said, that I'm going to use is entanglement. All right, so there's a fair bit of definitions here. So let me generally consider a state on a Hilbert space which has a tensor product decomposition in terms of the space inside the circle or disk and the space outside, so A and B. So the entanglement entropy is computed by taking the marginal or the trace over everything outside of the region of interest of the disk. And then you compute the von Neumann entropy of that density matrix, rho sub A. By the way, when I denote this rho in this tensor product Hilbert space, I'm actually being a little bit agnostic whether or not rho refers to a pure or mixed state, but I'll be specific as we go along. Okay, so that's the general definition of of entanglement entropy. And in a topological phase, there's a famous result for how that entanglement entropy of a disk, excuse me, scales with the linear size, capital L, of that disk. So there's an area law term, that's the first term here, which has a non-universal coefficient, which I'm calling alpha. And then there's a universal subleading term, gamma, which is some constant with respect to the size of the system. And for the specific topology here, where it's a disk, this subleading universal term is known to be related to some sort of topological information about the phase. So this log of some sum, the D's, they're called quantum dimensions of the associated quasi-particles which exist as part of this quantum phase. And what these quantum dimensions mean is, if you take a bunch of quasi-particles A, okay, these dimensions allow you to determine the asymptotic scaling of the many of the, say, n A particle Hilbert space. Okay, so for the Laughlin state, it's a so-called abelian state, and all these quasi-particles have quantum dimension equal to 1. So if you have a bunch of quasi-particles and quasi-particles, the Hilbert space that describes that is just one-dimensional. On the other hand, if you the other state I'll be considering here is the Moore-Reed state and various cousins of it. It has additional quasi-particles, in particular a Majorana, a fermion, and that has a square root of 2 quantum dimension and gives a more a larger n particle Hilbert space. By the way, this universal subleading term for the disk entanglement entropy happens to be related to the sort of generalization of the C theorem to 2 + 1 dimensions, the A theorem, which was studied in particular in these works. All right, any questions about these definitions? All right, so the entanglement entropy depends on topology of the space. So let me vary things up a bit. So now I'm going to consider the phase on a torus, and the various subregions will be cylinders. So the region of interest that I'm not going to trace over, region A, is just some cylinder subregion, and the other part of this, for this example, is just everything else. Okay, on that torus. Okay, so now one can redo this calculation of the entanglement entropy of subregion A, and in addition to this term, which depends on these quantum dimensions, there's a factor of 1/2 that differs. You find an additional term that I've circled, and what it depends on now is the amplitude psi sub A of the quantum state. So on the torus, the ground state is degenerate, and so you're free to put the system in any one of those degenerate ground states, and psi is just telling the amplitude to be in one of those particular degenerate ground states. Okay, so the point that I'm making is for a disk topology, you get some contribution to the entropy, which depends on these quantum dimensions. On the other hand, when you consider this cylinder subset of a torus topology, you get some information, or at least you get some sensitivity to the fact that the state is degenerate. So one of the points of this talk will be to reinterpret roughly the second term in terms of other entanglement measures. Okay, so the overview, the rough overview, in this first part of the talk, I'm going to give this rough overview, and then I'll summarize the results before justifying them to some extent. So the first statement is what I just said, which is this second term, roughly, which I'm calling the topological sector contribution, because it depends on the amplitude to be in a particular topological sector, psi sub A. It's distilled by the entanglement negativity, as I'll discuss and define. And then the second point of the talk is that this term here, it constrains the real space structure of the wave function. So just like if you're considering two-partite entanglement, the Bell state, you can't separate such a state. Likewise, this term, as measured by the entanglement negativity, constrains the real space structure of this topological phase, the ground state of the topological phase. All right. Any questions on that?
Hi, Mike. This is Francesco.
Hey, Francesco.
I have a question. So can you repeat what is this psi A in terms of topological field theory quantity? I didn't understand.
Sure. Let me just write it. So on a torus, the ground state is in general degenerate. And so the psi sub A are just the amplitudes to be in one of these degenerate ground states. Does that make sense, or are you asking for more than that?
Okay, yeah, it's okay.
Okay, that's all I mean. So yeah. Other questions?
No.
Okay. All right, so let's now start to get into it. So let me define for you some of these quantities. I know these were defined, I think, earlier in Shinsei's talk. So in the entanglement negativity. So what is this thing? So it's a measure. Excuse me. It's a measure of quantum correlations in mixed states, and on the other hand, you can alternately think about it as a measure of multipartite entanglement in pure states. So by multipartite, I really mean 3 or more subsystems. So how is it defined? Well, so again, I'm going to take my state rho, which I'll allow to describe either a pure or a mixed state. And the first thing I got to do is I've got to take what's called the partial transpose of this density matrix rho. And so to be specific, I'll take it with respect to subsystem A. And so the definition is just simply that the matrix element of this partial transpose is one where you just interchange, in this case, the first, the kets in the first entries of these states. Okay, so that's the key definition. And now there's 2 different sorts of negativities. It can be a little confusing. I'll try to make sure I don't lax on this. So the first is the negativity. So that's defined in terms of this one norm, and it's just the one norm of this partial transpose density matrix. Then you subtract 1 from it and divide by 2. So the point is, for a basically a separable state, or this one norm will equal 1, and so the negativity will vanish on any separable state. All right. Here, this is the one norm. If you wanted to adjust the subscript n, take the n norm, you would take higher powers of this object here. Okay, so that's the negativity. That's not exactly what I'm going to be talking about, but closely related. Instead, I'm going to be talking about the entanglement negativity, sometimes called the logarithmic negativity. So that's just the log of this partial transpose of the reduced density matrix. Any question on these definitions? So it's useful to have a simple example. So let me consider a system of 3 qubits, so C3, and it turns out that there's 2 distinct representatives of distinct 3-qubit entanglement. So these very famous states, W and GHD states, are written here, and what it means that these are the representatives of distinct 3-qubit entanglement. What that means, representatives, means that all states related by local operations So local operations just means, rotations of an individual, one of these individual qubits here. Okay, or CC is classical communication. All right. And then distinct 3-qubit entanglement, what that means here is that if you take the entanglement entropy of any subregion, so qubit, the first qubit, let's call that ABC, that they're equal in both these states. So for any subregion. All right. So the entanglement entropy of the first qubit of the W state is equal to the entanglement entropy of the GHZ state with the same qubit. Okay, but how these states differ, one way to measure their difference is to use the entanglement negativity. So in particular, just by, you can follow the definitions and compute and find that, say, the entanglement negativity of region A with respect to the rest of the system of the GHZ state is greater, or what important is that it differs from the entanglement negativity, of the W state. Or if you like, you can take, you can trace over region C and calculate the entanglement between the two sub-regions A and B. Okay, and again, those two things differ. Okay, so that's supposed to give you a little bit of intuition for the, or rather justification that this entanglement measure is useful. Okay, so what we want to do. Oh yes, please.
In these inequalities, the last two terms, what happened to C?
Yeah, good question. So in these ones, right?
Yes.
Yeah. So in these ones, what I mean there is let me write to be concrete. So sorry, I was a little unclear in that. So I've taken the trace, say, over that guy, and then I've taken the entanglement negativity of that object. Yeah, sorry, I used the same notation. Does that make sense? Does that answer your question?
Okay. While in the first case, you only trace over, BC in the first, element.
No, sorry about this confusion. Let me write a little bit neater. Yeah, so for the first case, really the first two guys, right? I'm just considering the density matrix of the full system. So the GHZ state would be. So this is my density matrix, and then I go back to the previous slide and compute this partial transpose and then the negativity. All right. For the second two cases, what I'm doing is I'm trying to measure the entanglement between regions A and B, but not knowing anything about C. So I'm tracing over region C to get a reduced density matrix, if you want, only in terms of A and B. And then with that matrix here, I compute the entanglement negativity.
At this point, this does not bring too much insight of what negativity is. Do you agree?
Yeah, so I would, I think I sympathize. Yeah, so I would just say it's something that, it's some object you compute and you get a different answer for these two states. Is that what you mean by it doesn't give much insight?
This I understood, but okay, but please keep going.
Yeah, I think I probably am in agreement with that sentiment, but okay. So those are 3 qubits, but I want to try to apply this formalism to topological states. one perspective is, because they're interesting and I want to learn all I can about them. Another perspective is that such states are, relatively simple examples of, interacting many-body systems, for which you can generally can compute a lot. And so this gives me, these states give me the opportunity to investigate these multi-point entanglement properties. All right, so
I have a question.
Please.
Are you considering bosonic states or fermionic states?
Yeah, so I'm allowing M to be an arbitrary integer. Okay, but yeah.
So for fermions, I believe it's better to use a fermion version of partial transpose.
Mm-hmm, mm-hmm. Yeah, that's a really interesting point. So yeah, it'd be nice to talk more about that at the end, because you'll see that this entanglement negativity will actually be insufficient to fully kind of characterize in a way that I'll make precise this second state.
Okay, yeah, thank you.
Yeah, it's a great comment. So yeah, and I'd like to learn more about that. Okay, so I'm now so I'm gonna be telling you about these, or rather I'm gonna be studying these two states, and here are the results on the next two slides. So I'm going to calculate and let's consider the left figure here. I'm going to look at this entanglement negativity of the so-called odd cylinder subregions of the torus with respect to the even ones. That just means region A, they are these guys, and region B are these other guys. Okay, and similarly for this second geometry here, what the second cylinder geometry means, it means that I've traced over this missing cylinder. So I've started with a torus, and then I've traced over what would be here. This, in the previous slide, this was qubit C. Okay, and Y here is just denotes the cylinder subregions of the resulting cylinder. And so what we find is that the entanglement negativity, just like the entanglement entropy, it depends on these amplitudes to be in one of these degenerate torus states, and then it depends on this factor C, where C is this ratio of partition functions. So these are partition functions for the edge states of the associated TQFT. Okay, so for the Laughlin state, this edge state partition function is just a free boson at some particular level M. And so what you see here is that this quantity that's appearing here is this ratio. It's the ratio of partition functions at two different quote temperatures, temperature 1 and temperature 2. Okay, so it's in some sense it's a comparison of, in a very rough sense, it's a comparison of free energies of a system at two different temperatures. Okay, so that's the result. And now knowing the edge state theories, we can calculate, and we did for this example, the partition functions, and infer a general result, which is, for the torus, this entanglement negativity, it has an area law term. It has a second term which depends on the sums of quantum dimensions, and then there's a final term here which depends on this degenerate torus amplitude. Here, now let me explain notation. M in the first formula here just refers to how many cylinders you've broken the torus state up into. So in this picture here, I have m is equal to 4. Okay, so that's the torus result that we infer from these two specific examples. For the cylinder, that is when we compare the entanglement between two different cylinder subregions after tracing out part of the torus. Again, it takes a similar form. There's an area law term. There's a term that depends on this sums of quantum dimensions, and then there's a final term which depends on which topological sector your starting torus state is in. Here are what that means. It is the number of shared boundaries of your cylinder geometry. So in this picture here, there are 2 shared boundaries. So R is equal to 2. And so what we did, we did this for general M and R, and for these specific states, and our results are consistent with previous work by Liam Vidal, Casanovo, and Wen Matsura and Ryu, who studied either abelian or non-abelian topological states. Any questions? So that's the general result in terms of the entanglement negativity that we got, and now trying to answer, was it sort of, what is it good for in some sense? Going beyond a sort of non-local probe or non-local characteristic of the state is, I'm going to now summarize. Are there any questions about what I said here or the meaning of these terms?
No questions.
Sure. Okay. So the idea has to do with monogamy, and the concept that I want to focus on here is what's called disentangling. So first, monogamy. So a monogamy relation is some sort of inequality defined with respect to an entanglement measure, which is supposed to tell you the degree to which a subregion A is entangled with other parts of the system. So you divide the system into 3 parts, and it's saying that entanglement, if A and B are strongly entangled with each other, then they can't be entangled at all with region C. So the simplest example of this is if you have 3 qubits, 2 of which are in a Bell state, then those 2 qubits must be in a product state with respect to the third. So that's monogamy, and disentangling is simply the situation where you have saturation of this inequality. In particular, subregion A has no quantum correlation with the region C. So the entanglement negativity of A with respect to BC is equal to the entanglement negativity of A with B. You might ask, how did you go from this negativity to the entanglement negativity here? Well, when the negativity vanishes, that's what this X is supposed to signify, then these 2 entanglement measures it means that the entanglement negativity also vanishes. Okay, and so this saturation, this inequality becomes a squared negativity becomes an equality of entanglement negativities. So for states which satisfy this so-called disentangling condition, there are some implications in terms of the real space structure of the state. This is real space structure because we're choosing to decompose our state with respect to in terms of space. But in principle, you could consider other sorts of decomposition. Momentum space decomposition of your state. All right. So for a pure state, if our state is an element in a Hilbert space where kind of this intermediate region, B factorizes. Then the disentangling condition measuring the entanglement of A with BC, or comparing the entanglement A with BC and A with B. When that condition holds, pure states are products. All right, so there's no entanglement between ABL and BRC. So that's pure. And now for mixed states, it's what you might have expected. When the disentangling condition holds for a mixed state, then it implies that this mixed state is separable. So separable just means that the density matrix of the system decomposes in terms of a sum of tensor products of individual density matrices on the subsystems, and the sum is over some probability p sub I.
Sorry, could you please show again what are the region A, B, and C?
Sure, certainly.
Thank you.
Yeah, so thanks. So here's the sort of example that I'm going to be obsessed with here in this talk. So I'm going to be thinking about torus, and region A is some cylinder subregion. And then there's the one that I'll focus on for this disentangling part. There'll be 3 other cylinder subregions, a left B region, a left B region, a right B region, and then the rest of the system, which is region C. Does that answer your question? Make sense? Or
Yes. I
okay. So the one one consequence of studying these entanglement negativities, and in particular this disentangling condition, is it's a way to determine whether your state is a product or separable for the mixed case. And so in this example, or in what I'll show, we're able to excuse me, construct exactly the ground state wave functions. And so in principle, you can just look at that if you wanted to know that sort of information. It's a little bit complicated to try to calculate this object, but in general, you don't know you don't know that. And so this gives an alternative way, or rather an invariant characterization of the state. So when we apply this formalism to the topological states and just use the formulas that I had in the previous slide, what we find is these 2 entanglement negativities which appear in this disentangling condition, their difference in general has a non-zero right-hand side. And the right-hand side only vanishes when this amplitude is equal to 1 for some A and 0 for all the other ones. So what it's saying is that our topological state, it satisfies a disentangling condition when the degenerate torus state is in a specific topological sector. Now, according to the results on the previous slide about how states should decompose if they satisfy a disentangling condition, you might expect that if our Laughlin or our Moore-Reed state, which I'll describe in more detail in a second, if they satisfy this disentangling condition, you should be able to disentangle them, write them as a product state roughly. We find that that's only true for the Laughlin state. For the Moore-Reed state, this disentangling condition is only a necessary one. So this is what the question about the fermionic partial transpose earlier. This is it's a great question, and has a lot of relevance, in particular, I think, perhaps to the second result.
Sorry, the condition is psi A equal to 1 for one value of A and 0 for the other, or
Yeah,
different?
sorry. Yeah, let me write that. I was a little imprecise here. Exactly.
Okay. And this is true for Dublin state?
Yeah, so you can choose it, right? So it's your choice. How do you put, what state, what torus state are you in? And so if you choose to be in a specific topological sector, then you're satisfying this disentangling condition. And you can then go look at your Laughlin state and find that indeed it can be written as a product. It can be disentangled. On the other hand, if you do the same thing for the Moore read, you can put that in a specific topological sector. But in this case, it does not decompose in terms of a product. So, and so that's what I meant by this being a necessary but not sufficient condition to disentangle. Does that make sense?
Really?
Sorry?
Because, I mean, if I think what is the form of the wave function of the torus for Laughlin state, I don't see this disentanglement and disentangling property because, I mean, it doesn't seem to be at all a product state. I mean, especially because you have this global part that accounts for the degeneracy, and this is kind of unique, not so there is something I don't catch by knowing the explicit form of the Laughlin wave function.
Yeah, okay. Maybe it'll become clear exactly what I mean when I talk about this specific construction of these states.
Okay.
Yeah, but your intuition in terms of there's a global constraint is crucial. And while you can kind of get around in the Laughlin case, you can't get around it in the Moore read case.
Okay, please keep going, please. Okay.
Sure. Okay, so that was really the summary, and now let me try to argue or justify some of those statements. So what I'm going to do is I'm going to tell you how I'm constructing these states. So I'm going to use this so-called cut and glue construction. Then, depending on the time, I'll give you a little flavor of how the calculations go. If there's not enough time, we can skip. And then in the final part, I'll give you intuition for why disentanglement occurs, at least in one case, but not the other. All right, so the approach that I'm going to use to construct these topological torus states, there are two different apparently equivalent approaches. The first is to begin with a collection of one-dimensional wires, which each host some number of non-chiral fermions, and then you couple them together in some appropriate way, and this highly anisotropy starting point flows via this relevant or strong perturbation that you add to the desired topological phase of interest. So the evidence for that topological phase comes from the fact that the resulting state has the correct edge or the expected edge modes. Also, there's a notion of quasi-particles, which in this form was empirics as kinks in the one-dimensional description. So that's one approach. The approach here that we'll take here is instead we're going to glue together cylinder states which are already in the target phase of interest. So I'm just going to, if I want to construct the torus, I'll, take the Laughlin state on a cylinder, and then I'll glue that in some appropriate way to another cylinder. And how many cylinders I use to create that torus, is up to me and up to, and it is dictated by the calculation I want to perform. So let me remind you, lightning review of the different edge state theories and how this formalism works out. So for the Laughlin, it's just the free boson CFT at level M. So I'm just going to write Hamiltonians here. And so we have our derivative terms in H naught. Here, phi is some compact boson radius. I'll take it to have radius 1. And so that's how I'm putting up the level in terms of its commutation relations. So this theory, just a collection of such theories, just describes a bunch of decoupled cylinder states. Now I want to couple them together to form a torus, and the interaction I'm going to add is something that tunnels an electron between these two edges. Okay, that's accomplished by this cosine operator. And the claim is when I add that perturbation, I get the torus state. So that cosine, this nonlinear term, I don't know how to solve it exactly. However, for our purposes, we can consider the limit where its coupling G is very large, and we'll treat it in a harmonic perturbation where we'll just truncate this cosine at quadratic order. And if we do that, then we get a completely solvable Hamiltonian, it's just free fields. And we can construct the torus state in terms of the cylinders, the cylinder states. So as we know, we Fourier decompose our field in terms of the circle, the cylinder circle, and the Hamiltonian, it decouples in terms of 0 mode degrees of freedom, and all the rest, all the oscillator mode degrees of freedom. And this is just quadratic, so we can solve it. And the resulting state is just something that depends on how many of these modes are filled, right? So it's some linear combination over these modes. So the exact details are not so essential, but the point is we have a free field theory in this approximation which we can solve, and the resulting state is some linear combination over the quantum numbers associated to the 0 and oscillator modes. Now what I've written up here is the interface ground state. So maybe the interface between cylinder 4 and cylinder 1. But from this interface ground state, we obtain the torus ground state. The torus decomposed into some number of cylinders. Here it's 4 cylinders by simply tensor producting these cylinder states together. Okay, so there are various details which I skipped over, but the rough point of this is that we can calculate exactly in the harmonic approximation the ground state, and in particular decompose the torus state in terms of cylinder states. More read is similar. Excuse me. So again, it has a free boson component, but in addition, there's the edge state theory involves a Majorana fermion, and in addition, the theory splits into so-called untwisted and twisted sectors, which are associated to the specific boundary conditions you place on that on that Majorana fermion. So the untwisted sector corresponds to when the Majorana has antiperiodic boundary conditions. On the other hand, the twisted are when it's periodic. Now, it's not just two decoupled, CFTs here. They're coupled together, and states are required to be invariant under a Z2 Z2 symmetry. Here, the way that Z2 acts is it's determined by requiring the electron operator of the theory to be invariant, or rather, if you stare at this electron operator, it's invariant under a Z2 transformation, and that all states be invariant under that is this Z2 symmetry. Okay, so it just flips the sign of the Majorana and shifts the boson by pi over m. Okay, so we can play the same. We can roughly play the same game as before. We at the beginning we have decoupled cylinders described by this initial Hamiltonian H0. But now we want to form the torus state, and we do that by adding a particular interaction, H1. And so again, the interaction we're going to consider is something that tunnels electrons between the two nearby edges. All right, again, that's a interacting or nonlinear term. Don't know how to solve that exactly. And so we're going to make an approximation, a sort of mean field approximation. The idea is this term generates a gap for these modes localized on the interface, and that gap is associated to expectation values of the two terms appearing here. All right, and so so this second squiggly equality is where we've taken this mean field approximation and written this interacting term in terms of quadratic or free or solvable, and the strategy is to solve the solvable model, but be careful that the resulting states preserve this internal, if you like, Z2 symmetry I referred to on the previous slide. Okay, if we didn't do that, we would definitely not have the right the resulting states would not have the right structure. Okay, if we failed to couple them by the Z2 symmetry. And so there's a technical way to impose this, if you like, correlation between the bosonic and fermionic sectors, and that's by a proper projection of the states. So again, the game is the same. We have a solvable Hamiltonian, and so we can, according to which sector we live in, we can again write out the torus state in terms of product of interface states, or said differently, product of cylinder states. And then we just have to be careful about ensuring that the Z2 symmetry is preserved in the resulting state. So for the antiperiodic fermion case, aside from adding quantum numbers associated to occupation numbers of these fermions, it largely follows the Laughlin case. The novelty occurs when we consider the twisted sector, which is associated with periodic boundary conditions of the Majorana fermions. In that case, there are zero modes, and we have to be careful to account for them. So the zero mode Hamiltonian is very simple and written in terms of Dirac fermions formed by Majorana fermions at nearby interfaces. The Hamiltonian is just the number operator, right? It's just a sum of number operators summed over the different interfaces. And so depending on the sign of G tilde, the ground state is either all these Dirac fermion states are occupied or unoccupied. In this case, it turns out for the sign G tilde is negative, the ground state is one where all these Diracks are unoccupied. Well, I mean, that's wonderful. Okay, we solved the problem in terms of the interface Dirac fermions, but the problem, an issue arises when we try to impose that projection, that Z2 projection that I referred to. That projection is defined in terms of cylinders, all right, not interfaces. And so this Dirac fermion, which is defined with respect to a particular interface, okay, we somehow need to change a basis so that the Dirac fermion refers to not a particular interface, but the pair of Majorana fermions that belong to a particular cylinder. Okay, so this is a basis change, and it turns out that the expression of our zero mode sector becomes some linear combination over cylinder Dirac fermions, where the sum of occupation numbers is an odd number. Okay. The point of this exercise, what I was telling you, is that this transformation allows us now to do a Z2 projection and ensure that these states belong to the physical Hilbert space. Okay, so that was a introduction to this cut and glue approach, or a summary rather of this cut and glue approach. And now the point is that equipped with these torus states as expressed in terms of the cylinder state, in terms of cylinder states, I can now, calculate the entanglement negativity. Okay, so the point is we've expressed this torus in terms of a cylinder state. And this equality that I've written here is for the Laughlin case, and I'll largely focus on that case just because it's notationally simpler in the remainder. Before I summarize, are there questions? All right, so what I should plan on is concluding in about 8 minutes or 5 minutes. Is that right?
Yes.
Okay. So so we've achieved this this torus state. Now we want to measure it in various ways. So this state at the top of the screen here, where the states are just labeled by various quantum numbers, zero mode and oscillator mode quantum numbers, we got to normalize. So when we normalize that this is where, if you like, these edge state partition functions begin to arise. If you stare at this equation here and imagine summing over all allowed quantum numbers, you see that all you've got is a free boson partition function. All right. All right. So the two results where the entanglement negativities are expressed in terms of edge state partition functions, or rather ratios of edge state partition functions, I refer to these as two lemmas, lemma 1 and lemma 2. I think it's not necessary for me to go over some of the intuition for these results. So what I'm going to do is I'm going to skip these results, but turn the page slightly slowly. Okay, so the way these things are proved, so remember, we want to take the logarithm of this partial transpose. It's proved simply by direct computation. And the point is, you just follow your nose, follow the definitions, and you find that the quantity of interest, this rho dagger rho, is diagonal. And so we can read off read off the absolute value of its eigenvalues, and again, following the definitions and the identification of really the amplitudes of these different states occurring in the torus state, there appears this ratio of edge state partition functions. All right, so on these slides, I'll post them later. I've given the examples, the simplest example of a torus in terms of 2 cylinders, or a excuse me, or a cylinder decomposed in this case in terms of 3 cylinders, how those proofs go. Let me cut to the conclusion, or cut to more of the results. So once you have these results and these lemmas where the entanglement negativities are expressed in terms of these partition functions, then it's just a matter of computing the partition functions in computing these partition functions, largely known results. And so, for example, the free boson CFT, the partition function can be written in terms of Jacobi and Dedekind functions. And in this limit, where the size of the circle is going to infinity, coincident with the size of the torus, you can use the modular transformation to extract the leading term, and from that, you obtain, for the Laughlin case, an area law term, some term that depends on these quantum dimensions, and then a term that depends on the torus state amplitude. Similar manipulations apply to the Moore Reed state. The result here that we infer from these 2 specific examples, the thing to note is, for the cylinder case, this second term is absent when the topological state has abelian order, because in that case we know that the dAs are all equal to 1, and so this sum here is simply this psi squared, and so this normalized wave function in this term vanishes. All right, so now we come to using these entanglement negativity calculations to tell us something about the structure of the wave function. And so the disentangling condition requires that our torus state live in a particular sector. And the way this works, we can get the intuition, that's all I'm going to give, by staring at these wave functions. Okay, so for the Laughlin, or the really untwisted sector state, we imagine cutting a cylinder in 2. Well, the quantum numbers of the left and right edge modes are largely independent. Now, there is a condition that the topological sector be the same, so the little a be the same. That was the comment earlier, which was important. That condition is being enforced by the disentangling condition, but other than that, there's no other condition on these quantum numbers. So this is this factorizes in terms of a product state. Now, on the other hand, the twisted Moore Reed state, that's the one where there's Majorana 0 modes, and there's at the ends of each, or on the edges of each cylinder here, there's a Majorana, which we combine to get a 2-dimensional Hilbert space for the Dirac. That's a non-local excitation with respect to this cylinder. Okay, so we can't cut through this because the state is living in some sense on the 2 opposite sides. Now you might say, well, why don't I cut in between the cylinders? Again, in that case, we can't do it because if you like, the bosonic quantum numbers are shared between nearby cylinders. So we find that even if we put the Moore Reed twisted sector state in a specific twisted sector, it's impossible to disentangle. That is, write it as a product state. So let me read some the summary and the open questions that I wrote. So the summary is this topological degeneracy, which one of the most fundamental properties of a topological state, is distilled by the disentangling condition, as written in terms of the entanglement negativity. Now, one question which was already asked, almost at the beginning of the talk, was: is there a generalization of the disentangling condition using some other entanglement measure which would provide a sufficient condition, or rather would measure the absence of disentanglement for the Moore Reed case or other sorts of non-abelian states? Another question is, in this construction that I summarized, this kind of glue construction, the correlation length in the system is 0. So we're in this strict topological limit. So really we should imagine there being a finite correlation length, and equations with 0 in them should be replaced by exponentials vanishing in the size of the system. But it would be interesting to investigate the modification of these results, in such a more realistic circumstance. And a larger question is, what's the nature of entanglement or multipartite entanglement? When that correlation length goes to infinity, so in gapless systems. So it's a usually open question. So thank you for all the questions and your attention.
So, are there questions? Yes, please.
So I have a kind of a general question about the appearance of quantum dimensions in the expression for entanglement negativity and Monogamy entropy. So is there any kind of difference to these quantities, or some kind of physical significance or difference when the quantum dimensions are integers versus they are irrational numbers? Because at least in some sense, the classification of anionic models using modular tensor categories, there seems to be a big difference when these quantum dimensions are integers or square roots of integers versus when it is more complicated, like in the Fibonacci model. So can we see something from the entanglement negativity in this case?
Yeah, that's an interesting question. So not that I'm aware of. So if I go back to, say, these equations here, the only thing that these things seem to distinguish is abelian versus non-abelian. But within non-abelian states, whether it's some irrational versus integer, that doesn't seem to be distinguished as far as I can tell. Yeah, it's an interesting question, but to me, I don't see a difference there in terms of these specific quantities.
Right, and maybe if I can ask one more. So usually, I think there's an entanglement bootstrap approach, right, where we try to use the properties of entanglement entropy of the ground state to kind of reconstruct the fusion rules and other properties or other axioms of a modular tensor category. So the entanglement negativity seems to know a bit more, right, maybe, than the Monogamy entropy. So do you think using entanglement negativity will help in that reconstruction procedure?
Well, maybe it's debatable whether it actually does know more per se. I mean, the negativity should know more because it's supposed to, by being a mixed state measure, it's supposed to only be sensitive to quantum correlations. And if you had two decoupled systems where the individual systems were in Gibbs states or something and had some classical entropy, the negativity wouldn't detect that, so it would kind of throw that away. So so the negativity is supposed to kind of give you sort of clearer picture of your physical state, right? But in this specific circumstance, for these topological states, let's, if I go back to these classic entanglement entropy calculations, these amplitudes are appearing, right? And so this information is in some sense appearing in these quantities. Now, whether or not you can, find an appropriate linear combination if you wanted of these entropies to extract, say, this term, I think for us, we weren't able to do that in a simple way. One statement of the disentangling is that the disentangling condition, this disentangling condition was able to extract this term, in a very simple way. So area law terms canceled, this, the total quantum dimension term canceled, and left behind the term that depended on the degenerate amplitudes. And furthermore, it was related to the structure of the wave function.
Right.
So so I don't think I'm really answering your question there, but I don't know. I mean, I don't know if it's, if it ultimately is a better, or a better measure, which will go beyond, okay, for topological states. For general states, sure, yeah, but for topological states, I'm not entirely sure, actually.
Okay. Thank you. Yeah.
Yeah.
I have a question. I mean, given that you reduce your problem to evaluation of property of edge states, why don't you? Would it be possible to consider a simpler system like a Kitaev chain, in which the edge states are just Majorana zero modes, and maybe you arrive taking different pieces of this chain, and then maybe you arrive to the same conclusion about disentangling, not disentangling the states, right?
Yeah,
So
that's an interesting thing. I mean, you can imagine, achieving that limit, by squeezing your topological state, the 1D limit, right?
yes.
Yeah.
So it looks like you have a one-dimensionless manifestation of the same phenomena you are describing, just with the Majorana zero modes.
Yeah, I think that intuition is right. Yeah, but I think you're saying a precise, you want to express that in terms of some precise calculation, right? So, but maybe if you focus purely on this one-dimensional model, you kind of throw away all the unnecessary stuff in some sense. Is that kind of what you're getting at? Maybe. Yes, interesting idea. I'm not sure. Yeah, it's worth thinking about in that, in that specific 1D context. Yeah, that does seem interesting. It would be a sort of different calculation though, right? Because if you do go to the 1D and you're considering, some, if I understand correctly, different subsets of that 1D line, right? That's different from considering different cylinder subsets of a torus, I think. So like, the half line versus the full line sort of comparison versus, one cylinder versus other numbers of cylinders. So the calculation is different. So maybe it will provide, different insight. But I'm not sure exactly. I'm not sure if that helped or not, but
said maybe you lost the second clap. Because my microphone went off. So
Oh,
okay, thank you very much. So let's repeat the clap. Thank the speaker again. Okay. Okay, and bye bye.
all right. Thanks. Thanks, Andrea.